I remember when I started reading it, I started with the introduction. And so far, at that point, I'd read some papers and some books, and I was like, okay, I'm ready for this. And I started reading. It's green. It's on. Okay, let's try this. It's leaving. How about that? All right, okay. And so, I was reading that introduction, and I realized I don't understand the word of what's going on here, and maybe I should think about doing something else in math.
A ringing endorsement.
That's right. But so then I went to Paul, my advisor, and I told him, I can't even read the introduction of this book. What are we going to do? And he told me, why don't you just go on to the next chapter and see how that goes? And and I did that. And, after trying to read that introduction, the atom spectral sequence and all atom spectral sequences seemed really easy. So, thank you. That was, anyway, the rest of the book was extremely helpful. And at the end of it, the introduction made much more sense. So, anyway, I should do this thing where I localize all boards at, so everything is kn local, where n is some integer and p is a prime, and they're going to be fixed. What I want to talk about is some Spanier-Whitehead duals in the kn local category, and so it won't be far before I tell you what am I taking the duals of. So let's just recall that there are these Lubin-Tate or Morava E theories. I'll just denote them by E. They're usually denoted En. They are some kind of completion of the Johnson-Wilson spectra E parentheses N. So there is implicit in this notation, it's not just the choice of N and P, but there is also a choice of a height N formal group law that I am suppressing throughout. But then the coefficients of this spectrum are the Witt vectors Fp to the N, and then some power series variables, n minus one of them. So all of that is in degree 0. And then there's a periodicity element that's in degree 2 or minus 2, depending on your choices. And if you don't know what these Witt vectors are, well, you could take the p-adic integers and adjoin a primitive p to the n minus first root of unity. So this is a really important spectrum because it comes as, well, right, so I guess a lot of its relatives have already appeared. So what this thing has is it has an action by a profinite group, G, that's these days, I guess, called the Morava stabilizer group. So this is a profinite group, and it has virtual cohomological dimension equal to n squared, where n is the same n. So virtual cohomological dimension means that up to some finite group cohomology, it has finite cohomological dimension. Okay, so this group acts not just on the coefficient ring, but also on the spectrum E via maps of E-infinity ring spectra. So this is an E-infinity ring spectrum. So that's the content of which order does Hopkins, Miller, and Gorse. So, all right. So we have that, and why this is really important is that the Kane local sphere is the homotopy fixed points of this guy, of the profinite group acting on E. Okay, so we want to understand things about the Kane local sphere, and that directly is hard because this G is a complicated group. E itself has homologically simple homotopy groups. It's even periodic, et cetera, et cetera. But the group cohomology, as well as like homotopical implications of that, are hard. And so in between these guys, there are some finite, sorry, what should I say? So here is E, and there's a long path here, but then there's some finite subgroups. So G without the boldface is going to be a finite subgroup. And so these homotopy fixed points for the finite subgroups are of medium difficulty in that it's easier to get them from E because computing this finite group cohomology, for example, is easier. Also, the structure of these finite groups is not arbitrary. They are rather restricted. And then, at least in principle, the sphere is finitely built out of these guys. All right, so then what I want to talk about today is understanding the Spanier-Whitehead dual of E this is in the Kane local Spanier-Whitehead dual, but then since I've localized all boards, I'm not writing it. So this object, this is what I'm trying to understand with its equivariant action. I won't come to a definite answer, but I will illustrate an approach that leads to interesting calculations, and then a conjecture that does actually give you a very thorough answer. Okay, so first, let's talk about. Right, so what do I want to talk about really? So here it is, you could say, well, this is what it is. The idea is that we want to write a duality statement. And in a duality statement, we're identifying something that's like the Spanier-Whitehead dual of E, which is contravariant in E, with something covariant in E, like E smashed with some kind of dualizing object. Okay, so now I'm going to try to figure out what that dualizing object is. So to do that, let's get a little bit deeper into the structure of this group G. So G has a filtration of open normal subgroups, which so infinitely many. So which display G as a profinite group. So then G is the inverse limit of the quotients by these open normal subgroups. So these are finite quotients. And this is an exhaustive filtration, so that the intersection of all of them is trivial. And you can write down E itself with the action as a colimit of the homotopy fixed points under these open finite subgroups. So So in some sense, this is the content of Devnat's Hopkins, their paper on these homotopy fixed point spectra, or at least part of it. So so we have, of course, this is a co-limit in the K and local category again. So we're localizing it again. So just because I'll be taking, right, so what does it mean that this is equivariant? This thing has now induced G mod gamma K action, and so G can act through this quotient, and then we take the co-limit. These maps are equivariant between them. So I'll write, to make things look a bit cleaner, I'll write E square brackets K to be this homotopy fixed point spectrum. And, well, these guys now have a nice duality property. They're their own Spanier-Whitehead duals. So there's a map. Of course, there's a natural map from EK to its Spanier-Whitehead dual. And this is an equivalence. It's an equivariant equivalence. And how does the proof go? Well, so what is this map? I guess I should first say. So the map is the adjoint to a pairing. Well, we compare EK with itself. So it has a multiplication. And then we want to land in the sphere, which is E0. And the map here is the transfer map. So this is homotopy fixed points for gamma K, and this is for all of G. Gamma K is a finite index subgroup of all of G, so there's a transfer map that way. So there's nothing exotic about that. And so we check that when we apply Morava K theory to this, this map, we get a perfect pairing. And what's this perfect pairing? Well, the Kn homology of EK is a set of maps from the quotient G mod gamma K into, so I guess the Kn homology is into Kn. So we have some map this way, and then you could figure out that explicitly what this map is. You have a function here, so f and g are going to go to, well, a sum over the coset space. I guess I should continue here. That's right. Right, so if gamma is in there, I guess the other purpose of these boards is if you're tired of standing, you can still keep going. I don't. So the point is that this is a perfect pairing. So this is algebraic. You can check that. So that implies that these EKs are self-dual. So so what does that give us? Well, let's put the things together and see. So suppose we had, say, L greater than, I mean, what I'm saying now is combine this result with the fact that E is the co-limit of the E case and see what that gives us. So if L is greater than K, we have maps from between the E case. So let's see, how do I want to write this? So there's that equivalence, and then if L is greater than K, that means the group gamma L is a subgroup of gamma K, and that gives me a map from EK to EL, and this is the dual of that natural map, so I'll call that restriction. And there's a way to make a commutative diagram here, and the way to do that is if you look at the transfer or wrong way map there. So I guess that is called Frobenius reciprocity classically. So this diagram commutes, and what that implies is that the dual of E is the dual of this colimit of E else, and that thing is the now limit under transverse to E else. Okay, so that's part of the. I mean, we could, you know, this is great, and it gives us a stepping point, because what we want to do next is to try to understand this better, and somehow to, I don't know, decouple E from this equation. If I want to say that this is E smash something that's a dualizing module, I need to remove E out of this system. And it's possible to do this by the following kind of maneuvers. So we have this description, and now let's plug in what we know for E, that E is that colimit over there. So that's the limit, well, of colimits okay. So what I want to do is change the order of all of these operations. Gamma L, all right, so let's, I said that G is has virtual cohomological dimension n squared, and any of its all of the finite group information that makes it virtual cohomological dimension n squared rather than cohomological dimension n squared lives in like finitely many pieces here in this filtration, right? So eventually these gamma L's have finite cohomological dimension. So that means that I can commute this homotopy fixed points past the colimit, and because I'll eventually that's what happens. So that's that. And then there's some more magic going on, which is that it's possible to commute the colimit and the limit. The information that goes into this is, so in addition to in addition to gamma L being finite cohomological dimension eventually, it's not, that far along the way. Also, eventually, gamma L acts trivially on EK, because, well, EK, how does it gamma act on there? It acts through these quotients by G mod gamma K, and so gamma L will get into gamma K as you move along the filtration. So so then that lets you do another step here also, which is you can rewrite this as functions from the classifying space of this into EK. And then you can also rewrite this as the dual slash K. And so what you end up with is, well, okay, there's the limit here, and then colimit under K. This may or may not be one of those magic steps, but it is doable, and you can rewrite this as just the limit of these duals. And so now I'm going to actually switch that and write on a new line. So that's the dual of the colimit B gamma else smashed with E. And so this thing here, we are going to denote by, okay, so I'll just write this as S minus G. This G is to me, this is by definition this object, and the notation is such that S to the G is supposed to remind you of a one-point compactification, and this curly G is to be the Lie algebra of the profinite group that we're working with. Okay, so in summary, what this does is this tells you, well, there's the equality. This is what I want. So that it identifies the dualizing module. So this is the this, or the dual of it without the minus. And why? So the whole symbol S to the G is that colimit, and the notation is chosen so that G looks like the Lie algebra of this profinite group, and S to it like the one-point, like this one-point compactification of it. That's here. And so why is this a sphere at all? Well, if you so this, let's just think about what the homology is of this guy. So those are the duals of these classifying spaces. So this is going to be limit under transverse of the cohomology of these guys. So this is group cohomology, and if we were dealing with a group with actual, well, actually, you can compute that this thing is just ZP when star is n squared and 0 otherwise, because you know what transfer maps do. So on dimension n squared, they're isomorphisms, and then in other dimensions they're not, and therefore in the limit they go away. So so this actually makes sense as a sphere. Okay. This is also the way that, for example, in Sayre's Galois cohomology book, the dualizing module of a profinite group is constructed. So this is not something extremely exotic. Yeah, I think so. Yeah. All right. So, okay, so you know, we could stop here, but this is not necessarily that practical because it's a little hard to put your hands on it. So we'd like to identify it further with something simpler. And so that's where the conjectural part of this comes in. So that's our linearization conjecture. And so what that says is this, that so SG, that's going to be just that colimit before taking the tool. And the claim is that, or the conjecture is that that's equivalent to the same kind of construction, except for instead of looking at the sort of we look at the underlying additive D algebra, and so therefore the complications from this multiplication go away. And if that seems too obscure, let's make it more explicit. So I'll write this as M add, and what's this M add? It's the M. M is the Dieudonné module, and with and sub add means with adjoint action, and if these words are not ones that you use nilly-willy, so let's be extremely more explicit. So so what's this group G? Well, let's talk about a subgroup of it, which is the small Morava stabilizer group. Well, that's it can be written down in terms of explicit things. So it's isomorphic to the following, to the group of unit in the following thing. We take the bit vectors again of S to the n, and then we adjoin a non-commuting variable S and mod out by some relations S to the n. This S is an nth root of P, but it doesn't commute with the elements in W. It commutes up to Frobenius. So if we did, if we multiply on the right, well, on the left we have to act by the Frobenius element on it in order to commute it. And then S is the units in here. So let's write this as the units in O. O is that algebra underneath. And so then M is just O in this way. Okay? So, but we see it as, so this W is of rank n over the p-adics. So we see this as having rank n squared over the p-adics. So that's the n square of the cohomological dimension. And if you, right, and so so then like conjugation action is also extremely explicit in this perspective. All right. Are there any questions about this so far? That's right. Yeah. So I guess here I mean that kind of of thing, and here I mean M add is maybe like a representation over of the group, and I'm just doing 1 point compactification. Now I don't know how to do a 1 point compactification of a p-adic representation, but the following does make sense. If you say if you restrict to a finite subgroup, and then it very well may turn out that this M is comes from an integral or p-local representation, right? So let's look at a finite subgroup. Then maybe M add is isomorphic as a G representation to well, let's put it this way. Well, no, it doesn't matter. To some M0 tensor with the rationals, where M0 is some p-local representation, for example. Maybe M0 is a p-local representation that's torsion-free, and maybe M add mod p is isomorphic to M0 mod p. So then I could take this real representation of the finite group, and I know how to take a 1 point compactification of that, and that's a sphere. Does that make sense? No. Oh, here, sorry. Yes, thanks. Yeah. Right. So if that's the case, thanks. I merged the steps. And then, so then we take M0 tensor R and P complete that instead. Yeah. Okay. All right. So so that's, I mean, this is the kind of thing that in practice will happen. So that's where I'm gonna go next. So we're gonna look at explicit examples. Let's see. So part 3. Is hopefully going to be a convincing, well, hopefully will convince you that there's something to be learned from this conjecture. So the example 0 is in fact the example where this is not a conjecture. So when n equals 1, the linearization conjecture is true. So there, it's really easy because G is an abelian group, the unix in the p-adics, and so this M is just DP with trivial action because there's nothing else going on. Conjugation by an abelian group is really easy. And so we get that the dual of E, G equivariantly, is S minus 1. Is the minus first extension of E. And so this, in particular, implies, well, the known result that the Spanier-Whitehead dual of KO is minus first extension of KO. So I want to talk about a couple of other examples where we're going to work very explicitly with in identifying these representations, and therefore the dualities involved. So for n equals to 1, things were really simple, but for larger n, we have to be a bit more systematic in how we approach this. So so I don't know how to approach the problem of identifying these guys for the whole group G at once, but we can sort of, in the spirit of doing K-and local homotopy theory by these finite subgroups as approximations to the K-and local sphere, I'll just concentrate on finite subgroups. And so, so G is now going to be finite subgroup. And then, well, I guess in the examples I'll talk about today, it's either going to be maximal finite or up to the sort of Galois part of here, more or less finite. So, sorry, more or less one of the maximal guys. So, yeah, so those are the most interesting ones. So what do we need to do? So we are wondering about what is this. So the conjecture is telling us that if we want to understand this G equivariantly, it's going to be S to the minus M and smash E. And so we need to identify what this right-hand side is. And so to do that, we should identify this representation and add, or it amounts to, well, we should identify it where, well, it is a representation of I don't know, okay, sorry. What we'd like to do is to identify this thing. Well, this is supposed to be an equivariant equivalence, so we take the homotopy fixed points there, and that is going to be an invertible module over this guy. So this is the Picard group of the homotopy fixed points of E, so this high real K theory spectrum. So these are invertible. Okay. So, so in some sense now the task is to, yeah. So that's what we need to do. And so how do we do that in a systematic way? Well, we have a map from the real representation ring of G into the Picard group of this guy. And so what does that do? It takes V and sends it to this one-point compactification sphere, smash E, and then we take the homotopy fixed point of that. Okay? And we know some things about this map. So one thing we know is that the regular representation of G is mapped, I call this map J for a reason. So the regular representation is mapped to 0 under J. That's saying that E is orientable for the regular representation. So that's one thing that we know. So it means that we can factor this map J through the quotient by the regular representation. But in fact, we can factor through a lot more. Well, at least, I mean, and we can identify in a number of cases explicitly through how much more. So let's do those examples. So let's say example 1 is going to be n equals 2. So we're at height 2. Oh, before I specialize, so note the map J is not just it's not just that. It's J is a map of pi 0 of a map on spectra. What's the representation? The real representation ring. That's the well, it's maps from BG to real K theory. And the right-hand side is pi 0 of a Picard spectrum of this thing. Right. So because it's a spectrum level map, we can then study, for example, there's homotopy fixed points. In fact, okay, let's do it this way. There is homotopy fixed point spectral sequences, I'll just say it in words, on both sides, and therefore we could study filtrations that come from these spectral sequences and see that lots of things have to go 0 on the right-hand side. But for n equals 2, we know that there is the string orientation, which tells us, in particular, in this situation, something's missing here. It implies that the 8 connected cover of KO is going to go trivially in. So that tells us that things in filtration, in filtration of, well, not specifically very specific height of this filtration are going to go to 0. A second example is going to be, well, P is going to be odd, and the height is P minus 1. So in this situation, we'll find that, well, it may not necessarily be true that before taking homotopy fixed points, there's a null map. There isn't. There's no more orientations. But we know that the J, so I'll write it this way. So this map is going to factor through something, and that something is, so we're going to only map to a finite Postnikov stage, where we mod out by the 2p connected cover. And so this is the thing. So what are the homotopy groups here? So there is pi 0 and pi 1, and there's pi 2, except now from pi 2 on, we're mapping into something that's p-complete. So we get to p-complete those groups as well. So we get to modify this. So let's put a twiddle on it. And then it's going to be 0, 0, then zp, and then 0, etc. again, up to pi 2p minus 1, whatever that turns out to be. And so then we get this factorization there. And so what turns out here is that we take this this group and then identify the regular representation. So let's call this something. Do I have a name for it? Probably not. Let's call this RO bar. So if we looked at RO bar and then mod the regular representation of G, this maps isomorphically onto pick of H, G. So that's, in this situation, that's verified. In other situations, it's close to, well, I don't know. We have some indications in some other situations as well. We don't have a uniform proof. And so once you have that, then we identify and add in here. Okay. And since I actually do have time at this point, I'll tell you how we do these identifications. Any questions while I'm erasing? Yeah. I guess a couple comments. One is, every time I said it's supposed to be an equivalence, I guess I was keeping track of the equivariance. So the conjecture was going to be that that's a G equivalence, and now G, as I'm saying it out loud, is ambiguous. So it's either the big G or the small g, but regardless. At this point, the statement is just for this specific spectrum, which does have a G action for the big Morrow stabilizer group. So both of these sides have a G action. And so I don't know, there may be a statement for, like, in general for G equivariant things. I'm not making that statement here. Does that answer your question, or? Okay. Yeah. Yeah, and right, yeah, yeah. Okay. So, right. So how do we identify these quotients? I'm going to merge these two, or rather not merge, but pick the intersection of these two cases for simplicity and do explicit things there. So n is going to be 2 and p is going to be 3. But this works for n2 and, well, not this. A similar thing works for n equals 2 and p equals 2. And the analog works for larger primes and n equals p minus 1 as well. So, so here I'm going to look at the group, which is a semi-direct product of a cyclic group of order 3 and a cyclic group of order 4. So this is maximal in that small Morava stabilizer group. But the Galois group doesn't cause any problems in these kinds of questions, so you could put that in as well. Okay, so there's ROG, and we have this map J to pick of the spectrum, and that's just, it turns out there's nothing particularly interesting in this Picard group. That's just, it's cyclic generated by the suspension, and so the order of it is 72, which is the periodicity of this spectrum. It also goes by the name of TMF. So we're identifying this quotient, which is, I guess I called RO bar. Okay, and that maps from BG plus to this this finite Postnikov piece. So let's think about that. So what contributes to here? So in KO there, we're going to have like Z, so that's invariant. Then we're going to have Z mod 2. Well, this Z mod 2 is now H1 of the group with Z mod 2 coefficients. And then there is a Z mod 3, and that Z mod 3 is now H4 of G coefficients in Z3. And that's it for this case. Okay, and so then the question is, what's this map? Or said differently, what kind of invariance of the representations are we seeing here? The first one is really easy. So what does this map do? So V goes, well, in Z, it goes to its dimension. And what's the second invariant in Z mod 2? Well, that's in H1 here, and that's the first Stiefel-Whitney class of V. And this last invariant, the Z mod 3 invariant, in this case, turns out to be the Chern class C1 squared over 2 minus C2. So maybe this is really a sketch of what's going on. There's really a filtration, and these things are, obviously, if your representation is not orientable, then what's the Chern class? So when it makes sense, that's what it is, and this is really just a filtration. Okay, but we can explicitly now compute things. We have that. So first we need to mod out by the regular representation. And so we find that, okay, so what is the regular representation? it's going, well, it has dimension 12, which is the order of the group. That's not particularly surprising. The first Whitney class can be computed as a determinant, so we find that that's a non-trivial class in H1, and then here we have some choices, and we'll find that that's it turns out that's what it is. So you just compute some characteristic classes of these representations, and then you'll find that, okay, so then you mod by this group, and you find that that's just Z mod 72. So this map is then an isomorphism, and now the question is, what is MAB? And you do the same kind of thing. So now this is a 4-dimensional representation, and to understand what it really, like, everything is extremely explicit, so you can restrict to the 3 primary subgroup and a 2 primary subgroup to determine these invariants, and you find that that's that the first Whitney class is 0, and then the other invariant is not 0. Again, this -1, and then you find that that number is the same as, well, there's this thing that we're modding out by, and then, so let's see, that's 48. And you find that that's, well, once you mod out here, we get that MN is -44. So the corollary here is that the Spanier-Whitehead dual of this guy is a 44 suspension of this spectrum. So this, as a statement, this form was already known. So I'm at the prime 3. So this was computed by Behrens in his paper on the K2 local sphere around like 2006, using some very explicit computations, including the homotopy of mapping the spectrum, smashing it with a type 2 complex. Yeah, so that was rather hard. At the prime 2, I'll just state the result as well. So for n equals 2 and p equals 2, we also get this, that the dual of EAG is 44th suspension. Again, the same 44. And this is, as I understand, also done by different methods, including more computations by Irina Bobkova more recently. At the general primes, we get a shift that's also explicit, and maybe I'll just write it. That's, if I find it, because I don't remember it, but so the dual here is, let's see, n squared times 2np minus 1 PHG. So that's for n equals p minus 1. So, yeah, I'll stop here. Thank you.